Physical science time. Physical science time. We're going to talk about, well, first we're going to talk about our bellwork, which we did yesterday but didn't have time to go over because it was abbreviated. The first one says, Peyton, would you mind reading it? And speak up a little so that the microphone can pick you up. It's on, like, pick up all the noises mode, but you just still need to pick up or speak up because you're kind of...
So the first one?
Yeah, louder than that, though.
Okay.
Read the question, too, please.
Yeah. Define Newton's third law and provide an example with the diagram.
Ooh.
When one object exerts a force on a second object, the second one exerts a force on the first that is equal in strength and opposite in direction.
Perfect. Before we get to your example, I'm going to show you something. A lot of times, to simplify this for freshmen, you guys know any freshmen? Simplify this for freshmen in the past, I have done things like this. So we will have, let's now hear your example, Peyton, and I'm going to do the example on the board, but I'm also going to, like I say, simplify things as I have in the past for previous year's freshmen. What is your example?
I did someone pushing on the wall.
Okay, but I already did someone pushing on the wall, and the last time we did this. That's okay. That is a good example. That's why I used it. I'm good at
a big rock.
Someone punching a big rock. Okay, that's fine. So we're going to draw Dwayne The Rock Johnson over here.
Oh, great. What a monster. You have to give him...
Oh, okay, he's a little bit misshapen, but that's he is a happy guy, though, so pecs. Okay, and someone, so I guess a normal-sized person. This is not a very flattering image of Dwayne The Rock Johnson. Who's the someone here?
Rick Barry.
Rick Barry. Very close.
We'll just draw Peyton because it's easier. Okay. That's
Barry's easy. He's bald.
There we go. Now it's Peyton. Okay. Or and Pat. This does not really look like punching, so I'm going to undo that for a second. Okay. So. Okay. Now it's punching. In previous years, and we're going to talk about this kind of in the way that I think makes it easy for freshmen to understand. And also in the way that it is reality. And they're not, the first one isn't wrong. I don't need to have this yet. I'm going to put it down. What is the action here? This is how I break it down for the freshmen. Break it down.
Punching.
Yeah, punching. Peyton. Punching.
Rock. Dwayne The Rock Johnson.
Dwayne The Rock Johnson. Rock.
You know why I punched Rick?
Whatever.
Trying to get in react.
Peyton punching Dwayne The Rock Johnson. What then is the reaction? I like this.
Knocking it out of space.
Hurts. Dwayne The Rock Johnson's.
I like to phrase that as what sometimes is called a chiastic structure in philosophy, where thing X happens to thing Y, therefore thing Y happens to thing X. So if the action is Peyton punching Dwayne The Rock Johnson, the reaction is Dwayne The Rock Johnson punching, and I know that word is not really going to be useful here, but
Dwayne
Peyton.
The Rock Johnson.
He's enacting a force back on Peyton. The kind of funny little way that helps freshmen understand is that we use the same verb in both. The other example I commonly use is, here's Angie. Angie kicks the ball. The ball kicks Angie back, right? That's the reaction. So action, reaction. Now I said this helped break it down for the freshmen, but what's true about this? I mean, this is true. It's not false. But what's really happening here? Are these separate things?
No.
The ball's like, ooh, I gotta kick her back. Dwayne The Rock Johnson's like, ooh, I gotta punch him back. I mean, that might actually happen. But that's a social reaction, not a physical one. Well, what's true? Are these things separate actions, actually? No, it helps us think about it. It helps us break it down, as I said. But they're actually two parts of one. What did we call it? It's not an action and a reaction, really. It's a, or an. What's the next word? Yeah, they're both forces, and they are two separate forces.
Yeah.
But it's a... We talked about this, fellas. Action. It's got a prefix. Something action.
React.
No, that's the one. That's this one. Interaction. Remember, inter meaning between. It's action between two well, I guess objects. Don't objectify the rock though. Okay, so that's our example. So importantly, what is the magnitude of the force in both directions, or in both cases? I guess it is also in both directions. It's the same. It's the same magnitude. Thank you. Sorry if you said it whispered, then Rhett just spoke up and took your answer from you. It's the same magnitude of force. So even if Peyton punches the rock like that, no, I'm sure Peyton can actually throw a punch. He can certainly bite. If Peyton throws a punch, it's the exact same force that applies back to your knuckles. So that's why, if you're going to be punching folks, this is not the point of this class, but you're going to be punching folks, punch them somewhere softer than your knuckles, because otherwise you're going to be just as injured, except in your hand, as they are. If, for instance, if you're going to be punching someone's tooth, then you're probably going to wind up hurtier than they are, because the tooth is a hard thing. The tooth does the tooth apply more force? Be careful. No, but the tooth is a harder object, and so it gives us. We talk about in physics something called impulse. It has the force is imparted on the tooth for less time than it is on the hand, and therefore it's. Yes, you have a question.
Punch him in the stomach.
Sure. No. Yeah, you could. Yeah, I mean, if you're worried, if your primary concern with punching is how hard your hand is going to hurt, first of all, probably don't punch them at all. But second of all, punch them somewhere soft like the butt or the tummy or the back of the thigh or something. But then that's not going to hurt them either. So I don't know. You have to balance it.
If you go low, it's going to hurt you even more.
Colton, simmer down. Colton.
Since we're on that fighting topic.
Oh, we're not really.
No. It's an actual question.
Okay.
So, if someone gets punched in the cheekbone and then you look at the person that punched them, why with that cut, would that be since the force applied on them was on too thin a piece of skin and it
there's this phenomenon in medicine called a laceration. Hi, Mrs. Miranda. You're on video camera.
Great. Anyway, I don't have a sub for Amanda Vogel, so I'm sorry I have to go to the elementary.
Oh, that's fine.
So she needs to finish her test.
Okay, so you can do that if you like that. Oh, you don't need that. You probably better not have to sit back.
I was basic
Nice. Okay. There's this idea, Colton. Thank you. Back to your question. There's this idea in medicine of a laceration, which people throw around a lot. In fact, I hear it misused a lot. People think that a laceration is just a cut. That's not true. That's called an incision. A laceration is specifically when there's blunt force, like not cutting, but like if you get hit hard enough that your skin splits because it's been, like this part of your skin moves more than this part, so there's a split right there. Or in the case of your knuckles, if you, you can certainly get your knuckles cut. Like if you punch someone in the tooth, for instance, that might give you an actual incision where the tooth itself does some cutting. But if you punch someone in the cheekbone and you get a bleeding from that, it's probably a laceration, which means that there was enough force here that the skin split open, tearing, not cutting. Yes?
Yeah, because if you watch MMA and stuff, they get
this places where your skin is really thin, your thin is really skin. The rap song.
Yeah, because they have
like your eyebrows, your cheek, your knuckles, places where you're thin. Oh, I cannot do it. Places where your skin is really thin are more liable to have lacerations. You're very unlikely to have a laceration on the bottom of your foot because it would take an awful lot of tearing force to tear that skin. You can get an incision on the bottom of your foot fairly easily. Okay, let's move on. Thank you. Do the forces in your diagram, we're talking about Peyton's diagram of Peyton here. Do the forces in this diagram balance each other? No. Why not?
Because Dwayne has way more mass.
Hold on. You're right that they don't, but you're not right about the reason. At least I didn't hear that you're right about the reason. They're the same exact force, but why don't they balance each other?
Oh, because one's living.
No. Forces don't live. No, they're the same exact force.
One's bigger.
No, they're the same exact force.
Same exact force except
Look in your notes. No, look in your force, or look in your notes. They're the same exact force. You keep saying things like
reaction.
Yes, that's true, but they're the same exact force. But why don't they balance each other? I told you to write this in great big letters. They are acting in opposite directions.
momentum. I don't know. Momentum. That's probably the best answer I've heard all day. So only answer.
This is review. I had specifically told you to write this down that everyone is confused about
Because
this.
they're acting on
Thank you. Okay, now let's all write down again. Now, someone in here goes like, oh, I already wrote it down. Obviously doesn't matter because not one of you could answer my question. So let's write down what Alexine just said. They do not balance. The forces do not, and I prefer to use the word cancel here because that's really how we think about it. This is not the correct terminology, but that is how the children tend to think about it. The forces do not cancel because, why, Rhett?
I didn't hear.
Why?
I didn't hear what you said.
Anyone, not Alexine. Someone surely heard her, and I've already said it now twice.
Cancel?
Let's work on paying a little bit better attention. The forces do not cancel because they act on separate objects. Write it down. I don't care if you think you already know it. You obviously don't. Write it down. The forces do not cancel because they act on separate objects.
Should I do that?
What can we do if we don't know something that we're all supposed to know in science?
Write it down.
Okay, well, yeah. Apparently that doesn't work quite well enough. What should you do before the test? This is all over the campus. Study your
Notes.
book and your notes and
Read the video.
read the video.
Read
Watch
the
the video.
video.
Okay.
The sick time.
Define momentum, Leo.
Can you read after because you're...
They act on separate objects. Define momentum. Yes, Justice, go ahead. Shh, Rick, it's on.
Momentum is kilograms times meters per second.
That's the unit for momentum. Yes. What is momentum as a definition? Peyton, you already answered once, so not you. I'm sorry, Peyton. Cyrus, go ahead.
Okay. The definition for momentum?
Yes.
How difficult it is to stop a moving object.
How difficult it is to stop a moving object. It is measured, as Justice correctly says, in kilograms meters per second. It's defined as how difficult it is to stop a moving object. Only moving objects have momentum. What objects have inertia?
With acceleration.
All objects
I
with
said
mass.
that. I said all objects.
All objects with mass have inertia. Only moving objects have momentum.
Yeah.
Calculate your momentum in kilogram meters per second if you are cruising at 3.5 miles per hour. So what are we going to have to do first in this one?
Well, we have to have a weight.
Okay, yeah, let's think of that first. We should. Our first step is always to write the raw equation, but in this case, we don't have one of the givens yet. We need to figure out what the given is. So we need to figure out our weight. No, mass. We need to figure out our mass. What will be the best unit for us to use for our mass? Kilograms will be better because we need to measure, it specifically said, momentum in kilogram meters per second. So we need to find someone's mass in kilograms. Let's do Dwayne the Rock Johnson. Let's just say
100.
Let's just say he weighs 440 pounds
Pure muscle.
of pure muscle because that'll be easier on the math.
Zero body fat.
440 pounds.
How many?
Pounds are a unit of force, but on Earth's surface, we can convert pounds of force to kilograms. It's a built-in conversion. In 1 kilogram, there are 2.2 pounds of force. 440 divided by 2.2 is, should be pretty easy. Well, what would 220, which is half of this, divided by 2.2 be?
Half of whatever that is.
Oh, 22 would be 10. 220 divided by 2.2 is?
20.
Wait, hold on. You just said 220.
I did. Yeah, because 220 is half of this, right? Yeah, pretty easy math. So 220 divided by 2.2 is?
100.
100.
100.
I knew that.
100, and then, so since we have to, we're going to double it, so it's now 200 kilograms.
stupid.
That was, I thought that was easy. P equals M.
Oh, we were dividing. I
So here's our equation. Here's our equation. Step 1, write the equation. Step 2, P
Arby's.
equals, yeah, Arby's meat, we got to put the meat on there.
Colton's favorite sandwich.
Substitute.
Substitute. What's the M?
That's
Mass, which is, in this
200
case,
kilograms.
200 kilograms. What's the velocity?
3.5 miles per hour.
Uh-oh. What are we going to have to do now?
Convert.
Convert 3.5 miles in 1 hour. I hope someone's writing this down. I see an awful lot of people not writing, which is very suspicious. Miles to, what are we going to convert miles to? What do we need the unit to be in for it to work
Meters
for our
per second.
meters per second? So let's go right from miles to meters, since I know what that conversion is. And let's also go right from hours to seconds. In 1 mile, oops, sorry, that's the wrong line. Forgive me. In 1 mile, there are 1,609 meters, and in 1 hour, there are 3,600 seconds. 3.5 times 1,609. Math, please, math boy.
Hey, math boy.
Math.
Oh, you got one, Peyton? Thank you.
What was it?
Well, you can you see it from there?
No, I
Why don't you hop over once?
160.
In the meantime, though, Peyton's going to do it too.
Wait.
What's that number for meters?
1,609. Questions so far? Do you see why these two things are, we have to do these? Yeah. We could, hold on one second. We could, I would hate it, but it would be fine to find, if we assume pounds are a unit of mass, which they're not, we could find the momentum in pounds, miles per...
15.64.
We could find the answer in pounds, miles per hour, and then convert the whole thing to kilograms meters per second. That would be possible. But first of all, pounds are a unit of force, so I don't like that one bit. This is better. Sorry, go ahead.
15.64.
15 point, we'll do 15.6 to, oh, that's still too many sixes. Let's do, all right, 16 meters per second, okay? So our velocity here is 16 meters per second.
We got 1.5.
P equals,
We got 1.5.
I know, I think that's correct.
I think 1.5 seems more correct actually, because I'm aware of it. Thank you for corroborating. 1.5. I think it's the easiest, the way I examine it is usually that the answer, meters per second, should be about half the numerical value of miles per hour. Not exactly, but this is better. So 200 times 1.5, that's very easy math too. What's 200 times 1.5?
That's calculator. This is kind
What's
of
2 times 1.5?
2 times 1.5. That's
3. So what's 200 times 1.5?
300.
300 kilograms meters per second. There we go. So Dwayne "The Rock" Johnson, moving at 3.5, cruising, I think it says, at 3.5 miles per hour, has a momentum of 300 kilograms meters per second. So this is the first one of these we've practiced. That really has no meaning to, but that's quite a lot of momentum. Yes.
I have a question on the homework.
We did that yesterday, so I'll talk to you about it after class. Let's begin our notes. I'm probably going to cut this video and then start a new one, just so my point in this was so people who are absent today, since there are quite a few, would have the practice they need for the bell work. But now I want to start a new video so that when you go to watch this for your review, you don't have to watch us do the bell work, although you could. Bye for now!
Yeah, I'm too hard.
Wait, physical